Thank you for joining us for today's webinar. I can see a few people trying to log in, so we'll just give them a few seconds to set themselves up and we can get started. And thank you to everyone who has logged in early. I hope you're all well and keeping safe. I will quickly introduce Walking Tree to anyone joining us for the very first time. Walking Tree is a technology-driven organization dedicated to crafting and deploying state-of-the-art cross-platform web and mobile applications, facilitating system integrations, and accelerating digital transformation initiatives. Our forte also includes proficiency in data integration, analytics, and migration from legacy systems to modern ones. Our comprehensive suite of business intelligence solutions across all domains empowers businesses to meet their data-centric needs with agility and efficiency. And I'm very happy to see quite a few of you from our previous webinars on generative AI. We are very glad to know that you're finding these sessions very helpful. Today, we will be speaking on designing LLM-based applications using LangChain and Llama-Index. LLMs have become a remarkable technology for generating knowledge and reasoning and are increasingly seen as a game changer for developers who want to create applications that were not previously possible. However, relying solely on LLMs may not be sufficient to develop truly powerful apps. The real potential lies in integrating LLMs with other sources of computation or knowledge. Our speakers will obviously share more light on this topic. And we will obviously have some time at the end of our session for your questions, so please leave them in the Q&A box. Today we have three speakers. Many of you might be aware of all three of them. Scott Siebold is our CTO for over 30 years. Scott has been an astute problem solver, entrepreneur, and technology leader, driving our organization towards a diverse range of digital and data analytics capabilities and a culture of client-centric innovation. In addition to his valuable guidance and insights, Scott actively shares his knowledge with our clients and the Walking Tree team, empowering them to confidently navigate challenges, leverage opportunities, and fuel innovative growth. Moreover, his passion for the transformative potential of generative AI is palpable, and we are thrilled to have him leading our team towards new horizons. We also have Abhilasha, whose illustrious career spans 2 decades, during which he has led high-performing teams in development of enterprise-scale products and applications. Her expertise includes over a decade of experience in driving the end-to-end design and development of complex analytic solutions for diverse industry segments. Her unwavering commitment to excellence, coupled with her deep understanding of the technology landscape, has earned her a reputation as a seasoned leader in the field. Additionally, her excitement for the potential of generative AI is contagious, and we are very privileged to have her on board as we explore new frontiers. Lastly, we have Shubham, who comes with a robust background in data engineering, artificial intelligence, machine learning, natural language processing, and Kubernetes. He is a senior software engineer with 4 years of industry experience and has a proven track record in designing Flutter GPT-3 based applications, building applications that leverage machine learning services to process videos, images, audio, and text, and creating a cutting-edge MLOps platform that addresses the limitations of existing platforms. Shubham's multifaceted expertise and hands-on experience make him a valuable asset to our team. And over to our agenda now. I'll just, before we get to that, just a quick reminder that we will be answering all your questions towards the end of the session, so please do leave them in the Q&A box. Over to you, Scott. How are you doing today?
Good. Thank you, Pranshu. Let me just switch over. And Pranshu, I think you had a box. I want to make sure I don't have have the same. So you guys, please let me know if I do. All right.
It's fine now.
Okay,
Yes,
looks
please.
good.
Yeah.
All right, good deal. Hey, welcome everyone. I'll tell you one thing, I still, and I probably say it every time, but every time I see that 30 years in my name of experience, it still shocks me a little bit. So I suppose maybe when I get to 40, the 30 will not have shocked me so much, but no, glad to have everyone and see some familiar names. So again, welcome back, and thanks so much for giving us your time. I know it's valuable. And, you know, we've been talking GPT and you know, different things around large language models for a few months now. And really just with even some recent things, right, that have come out, it's really kind of like, well, this is all good. You know, Chat GPT, it's great. We can type in a question and get some really incredible answers, and we can even get some code out of it, right? And it's a lot of times pretty decent stuff. So, but really, you know, how do we integrate it with our apps, right? How do we make it useful for not just something where we're sitting in a screen on a, you know, looking at a screen, typing in and saying, okay, let's type in a question or try to get some response based on us just interacting with it directly. So how do we, you know, really, how do we design an application around it and really use it in a kind of a programmatic type way? And, you know, as the title for the webinar really says, we're going to talk about using LangChain and Llama-Index today in achieving that. So what I'm going to do to begin with is, and I guess I could go to the agenda when I'm talking about this, but what we'll do is we'll start off talking about large language models and how they work. And then I'll go into LangChain, and then Abhilasha will follow that up with Llama-Index. And then thankfully it's her talking about it, but she'll talk about vector stores and their usage with LLMs as well. And then we'll kind of wrap it up with Shubham kind of giving his oversight of the whole webinar, but also a demo of the app and kind of walking through some code so you can actually see you know, how this is coded and how LangChain and Llama-Index are used in that way. All right, so let's get rolling. LLMs and you know, how do they work, right? So what is really an LLM and a large language model? And it really is it's a computational model that uses deep learning techniques to learn representations of natural language data by processing. And I mean, when we say massive, right? I mean, really massive, probably things we couldn't imagine even 5 to 10 years ago, but vast amounts of data, of text data. And they're capable also of the really cool thing, right? They're capable of generating human-like text, answering questions, or just performing, you know, natural language processing tasks as well. So trained using data sets, right? So we're talking tens of millions of parameters that extend into hundreds of billions of data points, right? So just, you know, just vast amounts of text data that's been used to train these models. So, and, you know, one example of that, as we all know, is like the Chat GPT, right? So, well, what in the world, how are these things composed, right? How do they work? And what's all this terminology we hear, and how do they really get there? So, and what I would say are broken down into really 5 different blocks, if you will. And really the first one is around tokenization, right? So, you know, what is tokenization? Well, you know, tokenization, that's hard for me to say actually. Tokenization is really the process of converting a sequence of text into individual words or subwords or tokens so that a model can understand them, right? LLMs usually are performed using, you know, subword algorithms that split the text into smaller units that capture both frequent and maybe even some rare words, right? And that approach really helps to limit the model's vocabulary size, and it also maintains the ability to represent any text sequence as well. So it helps us break those into the the frequent words in the text, as well as some of the rare. So it helps us start to get some things separate so we can then continue to process it, right? The next block is embedding. Right now, embedding, let's just say embeddings to me are usually like encoding. So in other words, we're taking text and we're encoding it into vectors. And what encodings are they're continuous vector representations of the words or tokens that capture semantic meanings into high dimensional space. So in other words, in context, they're able to capture in context meanings and put them into a high dimensional space. And that allows, what does that really mean? What that really allows, it allows the models to convert discrete tokens into a format that can be processed by a neural network, right? So that's how these large language models are working. And so it takes text and converts it into vectors, encodes it into vectors. So the embeddings, they're learned during the training process, and then those results are representations that capture really complex, right? So when we talk vectors now we can start looking at the really complex relationships between words, like synonyms or analogies, for example. And then the next block is attention. And, attention really is kind of like it says, it allows us to give attention on the right things, right? So with this, we can actually take and say, okay, what should we, in this text, what should we be really giving a high priority? What should we be giving attention to? So it allows for prioritizing the important things while maybe deprioritizing some of the less important things, right? So that really helps us in terms of really being able to cut to the chase in that text and what's important about the text, right? Pre-training, like we've talked about, I think several times in these webinars, the amount of data that's used for these pre-trainings is just astronomical. And the beauty of it is, with the pre-training, you've got a model that really, before you do anything with it, right, it's already been pre-trained on all these vast amounts of data. So we don't have to redo that every time we build something, right? It's already pre-trained. It's already got knowledge and got those relationships built within the large language model so we can use them. And then another really beautiful thing about LLMs and a block, the other and the last block we'll talk about is transfer learning. So as LLMs are training, they're learning, and what they're doing is able to transfer that knowledge, transfer that learning into the next learning block, right? So as this thing learns, it's be able to use and transfer that as it continues that process. So those are the major kind of building blocks for an LLM and kind of how it works, and all that is wonderful, right? So you can go in and you can, even with say ChatGPT, for example, as a representative of an LLM, is we can ask it a lot of questions. We can get some really cool in context things that are very detailed and useful to us. However, in context of our businesses, right, maybe not so much, right? Because it doesn't have all your data in your enterprise. Okay, so how do we take that, and how do we take that data from your enterprise and augment the LLM so that we can kind of have some context in context of your enterprise data? I mean, those, when we're talking data, enterprise data, we're talking things like raw files like PDFs or presentations, Excel sheets, and so on. And then it could be an API, right? So it could be that you need information from your Salesforce instance, or from Slack, or from Discord, and so on and so forth, right? Or maybe you've got a vector store of some sort as well, or maybe it's a SQL database that you need, that you got your data stored in. Well, that is really what we need to capture, right? So when we're developing an app, we need a way to do that. And what we'll talk about next is we'll go into a framework called LangChain and discuss begin that discussion on how we actually create apps using these tools. So like I said, LangChain will go through first, and then Abhilash will be covering Llama-Index afterwards. So let's talk about LangChain a bit. Well, LangChain is, if we want to read the marketing type material, right? It's LangChain is a great framework that provides different capabilities to use LLMs easily and can be used for developing applications powered by LLMs. And what it really means to me, and as we'll go through the different modules that comprise LangChain, LangChain to me is, man, it really gives us a way to take our data, and customize and really create an app, right? And maybe even kind of link things together, hence chain, right? So we can chain things together, as we'll see, in order to create some really cool applications. And honestly, we're starting to see a lot of these, right? These things that are being created, but it's just astronomical. I can't wait until even, I used to say, boy, a year from now, I wonder where we're going to be. Now it's more like, wow, where are we going to be in 2 months, let alone 12? So let's talk about LangChain and how we use that. And in doing that, what we'll do is go through some of these modules and look at kind of what it's made up of. And the first one, the first module is actually models. And, those consist of, different types of LLMs, so large language modules, right, which are really take text strings as input and returns the text string as output. And that can be really useful for text generation, summarizations, classifications, those type things. And another is like a chat model, right? So chat models work on top of large language models and their APIs, and they give us a little more structured, and they're a little more structured, and they can be specifically trained for like conversational. And if you've attended our conversational AI webinars in the past, you've heard a little bit about that, but it's able to take things like conversations, taking that LLM and putting a chat module on top of it, so we get conversational type behavior. List the chat. It takes like a list of chat messages as input and returns the chat message. So the other one being text embedded modules. So, and these modules, they take input and convert it into text embeddings, and it returns like a list of floats, for example. Well, the next component or module in LangChain is something called prompts, right? So, and you probably heard it before, and there's lots of cool tools out there, but prompt engineering is the new programming, right? So basically, what does this really do for us? Well, prompts allow us to even come up with templates. So the templates are a little more structured and give us examples of what we might ask or how we might ask something appropriately to get the best answer. Those could be things like maybe it's input from another data source. So you come up with a template and you insert a word from a data source, or it could be user input, right? But what these prompts allow us to do is it also allows us to come up with templates so that we're asking questions in the right way, to submit to our, our large language models. The next component is, and I'm flying through these guys, there's a lot of depth into these, but for the sake of time, I'm keeping it fairly brief. Indexes are the next component or next module of LangChain. And it's a library that facilitates these 3 steps that you see here in order to effectively use an LLM efficiently. And those are things like, text splitters. So we're taking your information and then being able to use those and embed those into and store your text in vector stores. And again, those could be things like, those could be documents, right? For example. And it's going to split those in and embed them, encode them, right? Encode them as vectors and store them into some vector store. And in this list, you'll see there's several different types for each of these. So like text splitter, you got character text splitter, or maybe you've got a Hugging Face length function of some sort, right? Maybe it's a Python code text splitter. And then on the embedded algorithms, you could be using Azure or Cohere, OpenAI. So you could be using various numbers, SageMaker, AWS, SageMaker endpoint embedding. So lots of different ways that you can embed, get data, and then encode that and create these vectors so that we can effectively use those to interact with our data and marry that up and interact with a large language model. And then the next component of LangChain is LangChain really has some really impressive memory types that it can interface with. And really what this, the key here with this is, if you look at this list, many different memory types. It could be something as simple as like, conversation buffer memory. That really like maintains the raw input of a past conversation, between the human and an AI as history, for example. It could be keeping up with chat history. But many types. So the point here being really, it has some really cool ways of utilizing different types of memory. It even has, conversational knowledge of graph memory, right? So it uses a knowledge graph to create memory. So lots of different ways, and as well as vector store, which we'll talk about vector store even a little more in this presentation. So lots of different, really lots of different memory interactions that it can use as well. So very, very useful, and I think that really sets LangChain apart in that way that it's able to pull from and store different types of memory. And then key to LangChain, of course, is change, right? So we want to be able to take things like prompts and maybe even sequence those with large language models. So we prompt for user input, for example, and use that to input to large language models. And really the list could go on and on and on, right, of how we link those things together. So it really, to me, just opens up just a world of functionality for our applications. And we can take, like I said, you can link different large language models together even, right? So that linking or chaining together, you can link different things to be able to create really one application that encompasses all those different things, whether it's APIs from different sources. Maybe you need to, for example, hey, I need my input, but I would also like to get information from, I don't know, something like Wikipedia or something, right? You want to pull data from there. It gives us ways to pull all those together and link them together in a sequence that makes our applications really useful. The other really cool thing about LangChain is the use of agents, right? So these agents help us in coming up with ways to say, okay, here's this data. Now what action do we take? So we can actually create things to say, okay, I'm pulling this data and I'm going to send a notification, for instance, or I'm going to look for another tool to pull in data from, XYZ. Maybe you need to do a Google search, right? Or maybe you need to go to Bing. Maybe you need to go to ChatGPT for something, right? But these agents allow us to be able to kind of pull all those together and help make decisions based on certain criteria that we set in our applications. So again, this is a very high level and very quick run through of LangChain. I think we'll get to see this in code a little more, and you'll be able to really kind of see how and the usefulness of LangChain. So that's just touching really very high level on it. And with that, I'm going to turn it over to Abhilasha to talk about Llama-Index. So Abhilasha, I'll send it over to you.
Yeah, thank you, Scott. Yeah. So thank you for the great introduction, Scott. So moving on, like as we saw, LangChain provides a whole ecosystem of many modules which together make it easy to use the large language models and also connect it to different data sources. Now, Llama-Index is another interface which actually provides the crux of how you use LLMs. So you can say that it has the central main points whenever you're trying to use an LLM, how you extend with the external data. So if you look at the high level flow of how Llama-Index connects to different data sources. So they have an impressive list of data connectors, and you can check that under the Llama Hub, where they have provided examples of these different data connectors. And once you have connected to your source data, so it could be file server, it could be a database. So once you connect, then based on the data, you would do some indexing. So as Scott mentioned, we would do the embeddings for the data, and we finally store it in a vector store. And on top of it, we have the query. So Llama-Index takes care of these things, wherein it provides you data connectors and it provides you indexes, which can connect to different vector stores as well, so that you get the embeddings for your data, and then you're able to query on top of that data. So if we look at how or what are the different indexes which Llama-Index provides, and this is more related to, you can say they are purpose-built indexes. So depending on your use case, you can actually match which would be the most suitable one, or in cases you may have to like combine more than one also to get the optimum results. So we'll look at some of the examples. So if I have to like list down, so we have the list index, wherein it's like a list as the name suggests, and then for any answer it goes across all the nodes, and that's how it synthesizes the answer. So if you have to like get an answer across multiple data sources, this is something you would consider. If you want to have like a summarized view of your data, and then based on the summarized collection of documents, you want to be able to get to the actual document where your answer lies. So tree index could be suitable for your case. A structured store index is suitable for cases where you have to connect to a structured database, like SQL database, for example. Then vector store, so again, when you are saving your index as part of embeddings. So this gives you a huge capability to do your search on a large corpus of data enabled by vector databases. And then you have keyword table search. So this is a variation of when you have like a disparate data sources, like different categories kind of data, where you can clearly segregate the keywords. So in those, and you would not want your algorithm to look for all the nodes. You can clearly segregate using keywords. And this is one of the ways how the indexing works. And finally, knowledge graph. So this is used to build indexes on top of your knowledge graph. So if you have a data in the form of a graph database, you can connect and do your querying on top of the data. So if you look at how each of these indexes are structured, so the node, the list index has the different nodes. So whenever we are like processing data in Llama-Index, it will first be like, first you connect to the source. It can be a simple document, so you use a document reader, or it can be like a, say, a Google Drive or a Wikipedia. So depending on that, you use the connector, you get the data. Then the data is split into nodes before it is actually indexed, and that nodes you can like leave it to the index to do it manually, to do it automatically, or you can manually provide like different text snippets so that you have control of what data goes into what node, so that like maybe you have, if you have different files, you can segregate it that way, or logically make your nodes so that the related things fall at one place, and that helps in the accuracy of the model being able to find your node appropriately. So now this is for a list index anyways. We know that like the base scenario is that the data is all over and you may have to look through all the nodes. So when the query is done, so it will go through all the nodes and then it will get the so one after the other, and then it will give you the response. So the output will finally be fed into the response synthesis part, is where you have the LLM coming in and like finally generating the response based on your inputs you got from the different nodes. And this is your your enterprise data which you have fed into your model by means of the list index. And here again, there are some variations where you can restrict or filter your query by providing some keyword filters. So then it would like restrict and maybe pick up only the nodes which have that keyword. So that would improve the efficiency of your query. So moving on, the next one, the vector store index. So as we know, like you're storing the data in the form of embeddings, and when you're doing it on a vector store, it will like fetch based on a similarity match and give you the top K results. So you can set the K parameter based on how much, like what level of data accuracy you want, and you can modify the parameters and decide. So finally, based on the similarity analysis, your data will be fed into the response synthesis and it will be generated. So again, you can provide parameters like the value of K, top K. Moving on, the tree index. So here, it's like your data nodes are built into a hierarchy structure, wherein the leaf nodes are actually your nodes, which is from your original document. But then there is a sort of summarization you can have on top of that to have some parent nodes, so that when you're querying, it will find the best route and pick up those set of nodes to generate the response. So you can set like how many branch factors you want to consider. So it will take the best, like one or two, depending on what you propose, and it will generate the best matched node and use it for your response synthesis. So moving on, so the keyword index is again like when you provide your data, it will set up like it will pick up the keywords from each of the nodes and then have a mapping for each keyword, like which are the nodes which have data related to that keyword. So the indexing itself will take place of this activity, and it will set up the mapping for when you're actually going to use it for the query. And obviously, since there is some sort of processing which is happening here, where you're trying to pick up the keywords and set up the mapping, so the token utilization will accordingly be higher for a keyword index. So all this activity, you can actually track the tokens getting used, and obviously you will have to see which is the most suitable structure you would want to follow for your use case. Now here again, when you're actually giving your query, so it will extract the keywords from the query and then match and find the nodes with those keywords. So at the time of search, it will be more efficient because it is actually going by the keyword approach. So it is actually like limiting the query based on the extracted keywords. Also, if you look at structured store index, so here again, Llama-Index provides these different packages wherein you are able to set up, say, a link with your structured store. So you can have data getting inserted to your database using this. You can query your database using text to SQL kind of setup. So in this example, if you see, so it is using a SQL context container builder, which is actually built on top of the SQL database. So you will have the database connection details and the tables you want to include. So you can limit those parameters, and then finally you can actually apply an index on top of the data also. So if you're directly going through the database, if you have a smaller database, if you have a larger database, you may want to apply embedding there also in order to get the benefits of a faster search. And that's why you can actually build index on top of your structured store as well. So here you can see this is a table schema index. Now this will help you query index for context. So you give the table schema and then you will give your query string, and it will fetch the corresponding result. So this provides you like a template you can use to connect to different structures. So if you you can actually do it similar with a pandas data frame, and have the capability to generate a pandas function also, pandas Python code. So some kind of structured operations can be performed using this capability on top of structured data, and also you can convert unstructured data into structured data. So those functions are provided as part of Llama-Index. Finally, so when with all these different ways of connecting and generating your indexes, finally it is how you synthesize your response. So again, there are a few options like create and refine is the default one, where each node will the first node will take the query and then generate an intermediate response, and it will go on to the next node and so on till you come up with the final response. So it's like a sequential flow of information, and with every node the response gets better and the node data is used. And here you have another way, which is tree summarize. So it's like it will pick up nodes and come up with a parent answer for like a set of nodes, and then similarly hierarchically processing come up with a final response. So tree summarize is a more accurate and more efficient way of querying. And there's another way also, which is called compact. So it goes with a compact approach, it does a bit of compressing the data as it processes through the nodes. Sorry. So moving on, composability is another very powerful aspect when you're using indices. So it allows you to combine multiple indices so that you get the capabilities and benefit of both. So you can have a lower level of index on your document, and then on top of the first level index, you can actually build a higher order index. And then when you're querying, it actually combines the capability of both and gives you a better performance in terms of speed and accuracy. So Shubham will be showing you examples on that. Also, finally, when we have gone through the processing, the query has come up with a response. There is a capability where if you want to add some additional logic on the data or on the response, you can use the node post processor, wherein it comes with different options where you can involve some keywords, or you can have some logic pre and post to whatever top K results were written, you want to check the previous and next also, or if you want to fix some recency parameter there. So all these extra capabilities can be added on top of your processed response to improve the accuracy of the results and to suit the requirements of your enterprise. So finally, if we look at the complete landscape, so ingesting data from different sources, and then you have the Llama Hub, where you have the data collectors, then the Llama-Index, which lets you index your data, connecting to the maybe the SQL's databases, and then indexing into the vector stores, and finally being able to query it, and then have some post-processing if needed, and finally give you a output based on your retrieved documents. And on top of it, you can have the capabilities of say ChatGPT plugins or the LangChain agent, which can give you a structure to your application or any other app frame. So like I will quickly touch upon the vector stores. So just because vectors are so important in all this, what we are talking about, because there's a lot of data involved here, and a simple SQL kind of traditional database will not suit our needs and will not be able to achieve the kind of latency it's required. So for all this high dimensional kind of search which we are looking for, a vector database is very much needed, and it provides you the capability to filter based on the semantic similarity, and you can actually give a geometric filter around the like using the different algorithms like the k nearest neighbor or the approximate match algorithms. So based on that, we can actually filter and get good latency on huge amounts of data. And for that, again, like in the combination or with the combination of Llama-Index and LangChain, you can actually connect to your vector stores. So the first column you see, it's like the normal. If you have your data already in vector stores, you can connect using the data connectors. If you want to build your vector stores and load it, you can do it through Llama. So Llama-Index also has different vector stores. Some of them are like inbuilt as part of Llama-Index, and then it also connects to the external ones. So you have the more popular like the Pinecone or Chroma, Fez. So all these different variations are available both in Llama-Index as well as LangChain. So how you choose the most suitable vector store for your requirement, again, you will have to assess and weigh all these different criteria. Like if you would want to go for a managed service where you don't want to have the hassles of maintaining your servers and scaling and deployments, and so you can go with a managed instance like a Pinecone, which is very popular, I would say, and which gives very good accuracy and performance. And you have other options also. So Viviet is one where it comes in both options. Actually, you can have a managed version, cloud version, and you can have a self-hosted version. And then you have like PG Vector, which is an extension on top of the Postgres database. And so depending on if you want to have a complete control on the hosting and what models you're getting used, you can choose the self-hosted version. Similarly, performance, so how well, what level of latency is being provided. Then existing MLOps, so how easily you can bring in your models. What is the way of like how you can give feedback to your model, how you can evaluate your model. So the entire ecosystem of how it works. Then the developer experience, so how well the API documentation is provided, how easy it is to get started up, how reliable and secure it is, and of course the cost factor. So depending on like if you want a more control and you want to do it on-prem or have better control on the costs, or manage where you don't want to spend on the maintenance part of it, but you just go with the paid version. So that is how you would decide. And so Chroma, Fez, PG Vector, so some of these are like to start with when you're building a prototype. It's easy to get started. If you know you want to go with a managed version, Pinecone is definitely a good fit. So you can assess your requirements and decide which vector store you would want to go, because definitely in this whole ecosystem, this is one thing which is very important and will play a major role in how well your application is able to perform and how easily it is able to respond to your queries. So with that, I would hand over to Shubham to take it forward on showing some of these applications. Over to you, Shubham.
Thanks a lot, Abhilasha. I'm sharing my screen. Pranshu, could you please enable screen sharing for me?
Let's see, Shubham. I think I'm.
Oh, you're a
covered.
co-host now, Shubham.
No,
You
I
should
can.
be able to
Oh,
share.
yes. Okay, good.
Thanks a lot. Hi, everyone. Welcome back. So as Abhilasha mentioned, I'll be demoing you certain use cases of Llama-Index. And I will be considering use cases from two different but related domains. One use case is from health tech and the other use case is from insurance. In the first use case, I'll play out a recorded demo because I've seen when I do demos at this point, when I do live demos at this point of time, particularly when I use ChatGPT, the model takes some time to respond. I want to cut short on that. The video was recorded a few hours ago, and that is playing well. The other use case, the insurance use case, which I will be demonstrating, will be more from the perspective of understanding the code and also the limitations associated with the current structure and the features of the Llama-Index and how we can improve them. So let me start with the first use case, which is related to health tech. So as Abhilasha and Scott very nicely elaborated, one of the most important features or the capabilities which Llama-Index provides us is to query our documents. And essentially, had it not been for these indices, LLMs would have remained very limited. Their uses would have remained very limited because there are a limited set of requirements where you need to generate new content. Most of the requirements, analytics-based requirements, are such where you need to understand and answer from existing content. So without further ado, let me start on the documents which I'm going to consider, which I've considered for this use case related to health tech. And these are domain-specific documents, intensively domain-specific documents. So what you see here is a set of documents related to orthopedic treatment guidelines, associated research, and physician case records. So this is a document, big document on standard treatment guidelines for orthopedics. And this document has got different sections. Well, this is by Government of India. And as you can see here, there are about 24 topics here. And this is quite an extensive document, right? Very well detailed. Another set of documents which have been picked up, these have been picked up from the WHO website. And other journals. So quite many of them are from important prominent medical journals also. And these are essentially research papers, as you can analyze in any way, as you can appreciate. These are really domain intensive. And unless you fine tune language models with domain specific text, it is otherwise very difficult to just do with prompt engineering and get answers to such complicated questions, as in having to do with research papers. Another document set which has been considered, another reference document which has been considered is actual physician case records. So these contain different attributes regarding patients in terms of their age, gender, the symptoms which they are facing, the treatment recommended, whether surgery is recommended in those cases or not. Now, in the video which I'm going to play out, in the demo which I'm going to play out, I will ask the bot different questions related to these physician case records, related to the research papers, related to the training guidelines, and we'll see how it returns the answers. I'll also elaborate on it as I go. So here I start. So this is Ikaya Conversational Enterprise Framework, Enterprise Conversational AI Framework, and I'm starting to ask it questions related to physician case records. So I ask it, show me top 5 cases of pain and swelling in the ankle. So if you go to the original document, it has a huge number of cases, and they're not meant to be related to ankles or to pain in particular. Those are general use cases which orthopedic, issues which orthopedic patients face. And when I ask this model, when I ask this chatbot to show me top 5 cases. So when you talk about top 5 cases, of course, it has to do similarity evaluation. It has to check which cases are related to pain and swelling in the ankles, and it has to rank the cases also. and it has to display the relevant cases. And I'm asking it to display the cases. I'm not asking it to rephrase them, or which I'll do later. But the idea is to essentially list out those cases. So this is pure embedding search. Of course, ranking the embeddings, ranking the answers with based on the similarity. Now, if I ask another question, what was the treatment for cases related to pain and swelling in the ankle? So this is a general question. I'm not expecting it to give a text, to give a section from the paragraph, as in from the set of paragraphs from the cases. It is giving a very precise answer from the document by looking at the cases related to pain and swelling and what was the treatment, what were the treatments generally recommended for that. I ask it, I don't provide a long prompt, I just ask it, was there a case related to hip replacement surgery? And yes, it shows that case. So you don't really have to provide it in a huge context every time. So the next question, because the documents are of different kinds, have documents related to training guidelines for orthopedics, have research papers. So it's worthy asking questions related to them as well. And here is a very domain specific question. And this question is about indications of surgery in certain cases of degenerative spine. So this is a research, well, not so much of a research question, but more of a treatment guideline related question. If somebody is facing certain symptoms, what is the way to establish that? So the question is, what are the indications for surgery in degenerative disease of cervical spine? A very domain specific question, and the answer to it comes from the document on treatment guidelines. And these are the indications of surgery which it points out. Now, it's not as if this sentence, these phrases are present in block in the document, relevant document. These have been extracted and have been put together, rephrased, and presented nicely here. Now, because I have research papers with me, I like to ask questions related to certain problems which have not been solved and the possible treatments related to them. So there is a medical condition in orthopedics, which is osteoarthritis, and I ask it to look up the research papers and suggest a possible candidate for treatment of that. I of course know that there are research papers which are talking about it, so I ask this question to it. But the way it actually parses those documents and gives me the relevant answer, it's quite amazing. So it recommends that there is this isorphy isorphy, which is in short is isorphy, which is a possible candidate. Well, so far so good, but I asked it, why does it consider it as a possible candidate for that? So it's a follow-up question on the same thing. So the above answer was, of course, taken from the research paper, but then it was a very short answer, and it was more or less, one could even get the answer from maybe the first few sections of the paper, maybe from the abstract of the relevant paper. So those are good number of research papers. But when I ask it, why is that considered as a possible treatment? So it has to go to the relevant sections. It has to rephrase the relevant sections according to my question, and it is able to do that. So essentially, somebody who is using these technologies will not have to bother about just being directed to the relevant text without your answer getting organized. So your answer has to be readable also. Now, I asked it a subsequent question regarding a particular kind of technique. That technique is also being discussed in documents related to orthopedic treatments, and because these are research papers, they constantly publish latest results of different research being carried out related to different treatment, new treatment guidelines. So this is something which is meant to actually come from the from a certain research paper which talks about a treatment known as a problem known as RPTK, and it talks about the effectiveness of SGR technique in treating that. So the research papers which I've shown do refer to some of it. Now, again, it gets the answer in a very precise format, and this is not something which you would rather get from the document just like that. I mean, you would have to fetch the relevant content and rephrase it. Now I have another question, which is a general question. I mean, it's not necessarily related to a document. It's a question on arthroscopic surgery, and the model, the underlying model answers this question well. So this is, of course, underlying models. So one can use different models with respect to LangChain. So what we are talking about today is LLM-based apps. These are not necessarily GPT or Chat GPT-based apps. So there could be any LLM underlying a given application, but then in this use case, the LLM was GPT-3, and for this last question certainly, and this gave a very generic answer. So it wasn't meant to be a document specific question. It was a generic question. So what I've tried to illustrate here is the fact that even on these domain specific documents, these models, this chatbot based on models which are being utilized through LangChain and Llama-Index, is able to answer questions very precisely and very accurately as well. And the best part is, these are domain specific documents. See, these are research papers, and these are very, I would say, very dense research papers. So if you were to apply the same technique to other fields like say, well, insurance, which I'll also show, but other domains like pharmaceuticals, which it is partially related to anyway, but still other industries like, of course, advertisement, media, gaming. If you have documents related to Bitcoins, etc., you'll see these things. So maybe I'll play another short demo, but that's not for demonstrating a very specific use case, but for just showing that you can take any document on the fly, upload a document, and get answers from it. I mean, you don't have to really keep documents pre-processed to actually derive answers from them. So what you have here is a very simple sample application where you go, let me play that again. You can upload any document of your choice, go to the application, take a file. Here is a file related to Bitcoins, which has been taken. You simply submit that record. Of course, internally it processes it, creates indices, and then you ask it a question related to that thing. So this was a document on Bitcoins. So an intensive question related to Bitcoins is asked. It's not just what is Bitcoin or what is blockchain. It asks a specific question, and as you see, it returns a response, and the response is as per the question, and it also gives you the source. So what I'm trying to demonstrate here is by this shorter video is that you don't really have to actually pre-process content, store content in a pre-processed way before you are able to query it. You can upload any number of documents from your side. The indices will be generated on the fly, and you can query those indices there. Now, let me go to a more involved use case, which is related to, I mean, not from the domain perspective, it's more involved from the tech perspective, because it is related to composable graphs. But the purpose of demonstrating that use case is to understand even the limitations of the existing set of indices as they are, and how we can enhance the indices, custom enhance the indices, and remove those limitations. So people who work in this field, I mean, people who are passionate about LLMs, who have been using LLMs for many months, well, if not years. I mean, those who have used GPT-2, etc. earlier, they have known them for years. But people who have used LLMs constantly, they have a certain experience with tackling certain kinds of outputs in specific ways where they are able to overcome the limitations. So before I come to the limitations, I would like to show the features. I'll also like to talk about how this thing is being done internally, so that we fully appreciate what is going on. So I will be starting to talk about the code which is playing out at the backend. I will not be, of course, going through each and every line because we simply don't have the time. In fact, we are shooting 10. I'll try to be concise, but I still wanted to be representative because I would feel this is the crux of the webinar. So this entire framework, the chatbot which you saw, has been implemented in Rasa because I wanted to try different modules together, and I thought it's easy to actually integrate them as part of a conversational AI framework. Not that one couldn't do without it, but it's easier done that way. So I'm just importing the respective modules from Rasa for that. But coming to the LangChain and Llama-Index modules, so I import the simple vector index, the simple keyword table index, and service context, along with the LLM predictor. Now, simple vector index, as Abhilasha mentioned, is one of the most basic way of indexing your data, where you given a document or a set of documents, you pass it to this function, or to this method, so to say, and it creates indices from your document or set of documents. And of course, there are more complicated indices, more complicated, or rather more useful for certain requirements, indices which are more useful for certain specific requirements, like the simple keyword table index and the tree index, which I'll discuss shortly. But I essentially import them, and I'll talk about these indices more when I come to them, because otherwise, taken out of context, it's difficult to appreciate the relevance of them. In this use case, I'm using OpenAI chat models. Now, one of the best things about LangChain is it allows you to plug and play with any model of your choice. And these models need not be, as I mentioned earlier, they need not be OpenAI models. They could be open source models. They could be models which you have picked from Hugging Face. It's easy to plug and play with these models. So here I'm using a category of models which is known as chat models. Of course, it's the chat models which have been recently more popular ever since the emergence of ChatGPT. And of course, the subsequent models like GPT-4 are also in the same category. They are in the category of chat models. I will be demonstrating the composability framework, where we actually build indices over indices for our requirement. And in that, I will talk about composable graphs. And let me start with how I ingest the documents. So the documents which I have for this use case, those are related to insurance. If I just give a quick walkthrough of the documents, just to make you appreciate the domain which we are considering. So these are documents related to insurance plans, and these are amongst prominent insurance providers in the states. So here is this document on insurance plans, or rather policies provided by Aetna Health Fund. You have another on plans by Blue Cross and Blue Shield, and there is a third one by Cigna Health Insurance. So these are again the extensive documents, and they have good details in them. And these are PDF documents. So as Abhilasha was mentioning, you can essentially read different kinds of documents. You could read text documents, you could read documents which are in image format, you could read PDF documents. Now, to start with, LangChain had the default capability for text and documents, but over time, more and more sources have been integrated. I mean, that's the beauty of it. That's the beauty of the framework. It is growing at an awesome pace. And so essentially, loaders have emerged for different kinds of documents. And what I'm using for this use case is the PDF loader. So, so when you go to LangChain website, you see a section on loaders, and there are numerous loaders for this use case because I'm parsing PDF documents. So I'm just using the PDF reader loader from the download loader method of Llama-Index. And so of course, because I'm using chat models, these are OpenAI models, I got to provide a key, which I've masked here. And I have these documents available to me in my folder. So there is this folder on health insurance where I have kept all the relevant files. And so this folder is on another system where the application is deployed. So the name is slightly different. Please don't get confused by that. But essentially, the idea is same. You have a folder where you have documents, and you are essentially trying to retrieve each file and building an index on top of it. So the idea here is to get the list of all files. And why to get a list of all files? Why do I not simply combine them into a single file? Because I want to get sufficient detail from each document, and at the same time get an abstract from all the documents. Because I want to get a sufficient detail from each document, I'll still keep it at the document level. So I get a list of documents. I'm doing a splitting here on the names of the files, because in this particular use case, as I'll show you later, I will be building indices, and I'll be building keyword indices because these are documents related to insurance. The names of companies are sometimes bigger, and I don't need to keep the names of plans. They are also big. So it gets complicated when doing keyword search. So I'm just splitting and I'm just taking the first part of it. It's easier that way. And there is no unique format, by the way. I mean, you can choose the indices you want to create, the keywords you want to add based on your domain and your requirement. So I have a dictionary here, and in the dictionary, I will be adding the indices, which I will be making from the different sources. So essentially, I'm using the loader method from there. I use the load data functionality within that, and I pass my documents, and I'm doing it for every plan. So for all the three. So in this case, a plan is an insurance provider. So you have Aetna, you have Cigna, and you have Blue Cross. So I use this functionality for loading data. I essentially provide the folder where my documents are, and I provide the full file path through that. And this data gets loaded, and then I'm defining an LLM predictor. Now, as Abhilasha and Scott were mentioning, LangChain will enable you to plug and play any LLM. So LLM predictor will help you specify what kind of LLM you want, and also different attributes of the LLM. So in this case, I'm mentioning that I want an OpenAI model, and I want a chat model. And I'm also mentioning the name of GPT 3.5 Turbo. I mean, I could have mentioned GPT-4 also, but in this case, it's Turbo, which I'm using. And I have recommended temperature as 0. Now, see, these are not a temperature 0 suggests some more deterministic output. So these are not when you pass from actual documents, you essentially don't want to generate stories, right? You don't want indeterministic answers. It's not generating poems where you would like a new flavor every time. It's like one question, one answer every time. So you want it to be more disciplined. So I get that thing done. I get the specific temperature provided and the model name provided, and then I ask it for other features. So I actually specify other features. So the kind of LLM you want to choose is certainly one important aspect, but then you would also want to provide other attributes like what is the chunk size limit that you want. So essentially, what's the number of chunks that you would expect to be generated in the output? What's the limit? Of course, you would not rather want your output to go on and on and on. So even people who have been using LLMs, in particularly GPT-3, they know that you need to provide a limitation on the output. This is as required by the model. Even if you don't provide, it will still display within the specified limit. But then in your use case, you still would want answers to be retrieved in a certain limit. Now, there are cases where you would want answers to be more detailed, but then one has to think through those cases and choose the limit accordingly. For example, if you want more detailed answers, then better first get some rise points and then ask your model to build on those points one at a time. So you actually get in loops. So, but still at the end of the day, you have to provide a limit. Otherwise, default limits will be considered. So I start building vector indices here. I'm using GPT simple vector index. So again, as Abhilasha mentioned, depending on your use case, you would go for vector databases like Pinecone, FAS. But in this case, to keep it simple, because the idea is to demonstrate indices, I'm using GPT simple vector index. And what it does is it looks at the respective document which has been ingested. So in this line, I'm creating a dictionary. I already have a blank dictionary. I'm adding the plans for the as keys in the dictionary, and I'm essentially fetching data from the PDFs through this loader.load data method. And when I do that, once I've done that, I pass this information to GPT simple vector index. Now this data is in a format which can be ingested by GPT simple vector index. If you just pass the PDF, it won't ingest it, because that format is, to start with, not fully compatible with the structure required by the index. If you were to pass test documents, it would still ingest, but you are passing PDF, so you need to do the right processing. So now I'm creating an index. Now I pass it a service context here. Now, why do I need to pass the service context here? Because service context also enables you to specify other information. So in this case, I haven't specified. So when you are creating an index, what is an index essentially? In an index, you have embeddings. So whatever you are passing, that content gets embedded. And there are different ways you can do embeddings. You can use, in this case, the embeddings which are being used by default are OpenAI embeddings. So it's text ADA 001, which is being used. I think 002, which is being used because it's the most powerful model for embedding. It's a default embedding model. If in case you were to use a custom model for embedding, in case you were to use Hugging Face, you would have provided that in the service context. So it's important. We are fetching service context here because there are cases where we don't want to go by the default embedding method, and it's helpful. We must, it's needed, it's a must that we provide that information in the service context. So we use that, and essentially we then, of course, when we are creating the index, we will get an ID for the relevant index where the embeddings are stored. And in this case, we are providing the name of the file or the plan, the section which we are extracting from the file name as the name. And then we also save it because naturally we don't want to generate it every time. In this case, I am doing that because I want to demo it. But once you have these indices, because when you generate them, these are not open source models. In this case, it's open at costs, right? The charges are very minimal, but still, it's important that we save indices. And it's not just about cost, it's also about processing time. So next what I do is, now comes the next big game. And so far, what I've done is I've extracted the documents, ingested them through the PDF loader, created indices by using GPD simple vector index and OpenAI embeddings. But now I have to actually build indices on top of those indices. So I have 3 documents. I need to answer questions from those 3 documents, but I also need to maybe compare those documents. So when I compare those documents, I don't really need each and every detail from each document, because that way I won't be able to compare. It's too much for comparison, right? Even LLMs don't do that. They have a specific context size. I mean, you can't just pass any length of input to them. So we will be creating indices which will be storing summaries, and essentially we will be specifying that for a certain index, one will be able to use that. One will be able to use a certain index for getting to the details of the document, but then there will be other indices which one will need for getting abstractions around those documents. Now, in this case, so far, in my dictionary, which I create for index summaries, I specify that this is content specific to each plan, and you should use this index if you want to look up specific facts about the plan. But then going forward, we will create composable indices. So what is composability? Composability, as Abhilasha was mentioning, is the feature whereby you can actually build indices over indices. You can add indices in that sense. Now, what I'm doing here, because I essentially want to query, or rather do inference on multiple documents, I want to compare multiple documents. So I just can't actually look at the most granular detail. I would rather need to summarize them. So what I do is, on what basis do I summarize? I mean, there has to be a good approach. So what I'm doing here is I'm using GPT simple keyword table index. So how will it be done? How will the processing happen? Whenever you ask a question related to a set of documents, which involves more than one documents, then your framework has to know which document it has to go to. And it just cannot look at each and every word of the document, right? To do the matching. It looks for certain keywords. It's easier to be able to locate a relevant document when it has keywords. So what I'm trying to do here is, based on the vector indices that we have already stored, I'm creating a set of keywords. And now I'm, of course, also passing this the summary feature here so that it retains that info. So this simple keyword table index will help you to find the relevant documents based on the keywords. Now, there's both a pros and cons. Pros is your search will be faster. The tokens which you will use will be lesser. But the cons is, if it comes with some random keywords, which are not necessarily something which you prefer, then you will also lose the information, which I'll show to you shortly. So the recommendation in this use case is to rather force it to use certain keywords. Now, we have another index. So this index was for summarization. Now, when we start essentially putting it together using the keyword table index, then we mention that the index which we are building, the root index which we are building, the root summary which we are building with the root index is one where we have details about multiple plans, and we should use this index if we want to compare multiple plans. Now, of course, when you want to compare multiple plans, you will go at the higher level abstraction rather than the detailed information about each plan. Now, I'm using something known as query transform, and this is a very powerful feature provided by LangChain. but then it's a double S word. When it performs superb. And when it doesn't perform, you won't even get basic answers to your question. And one has to intelligently see whether or not to use this feature, and if yes, how to address the limitations. So what is a query transform? So as the word suggests, it is transforming a query. Now, what's a query? A query is your question. Everything that you ask to your chatbot is a question. Now, what does query transform do? If you ask it a question, a general question, say, how is the weather, right? Or how are you doing? Or how has the day been? These are general questions, can be answered easily. But suppose if one were to ask a more complicated question, how has God blessed you today? Or something like that, right? Which is slightly more complicated. It's essentially asking the same thing. How is the day? Has something special happened? But then you ask it in a more complicated way. And this was still an easy example. I mean, people can do it 10 kinds of complicated ways, right? Query transform essentially helps convert those queries in a simpler format, where the answers are likely to be retrieved faster, as well as the answers are expected to be present in a document, as in much more expected to be present in a document. Now, again, when we do query transform, we are again using GPT 3.5 for doing query transform. There is no guarantee that the questions that query transform will come up with are actually relevant to your use case. And that is where we would need to add another filter from our side. This is what we do as customization and Llama-Index, of course. And for any real use case when does that. So whenever it generates a question, you would still need to see whether the question is similar to your requirement or not. As I'll shortly, so there are cases where it generates absolutely random questions. So overall, on an average, right, if you just average out on the entire set of questions which you may be asking, it is still helpful. But then there are cases where it just doesn't allow you to get answers from your documents because the transformation which is happening is not relevant to your question at all. So and again, this decompose transform is an optional feature. It's used because, of course, there are cases where in domain-specific documents, the questions you ask needs to be translated into a more simpler question. But as I said, it's a double S word. So when you do that, you will, in the query config, where you will specify the decompose transform, you will pass certain parameters, and well, in the interest of time, I will skip this part of query configs, but I'll move to the next where I'll just show the demo. So essentially, so when you are even doing decompose transform, you have to mention what is your structure type, whether it is a simple dictionary, as in case of simple vector index, or it's a keyword table, because of course, the questions it will also produce, right? They will be dependent on that. If it knows that you are going to use keyword index, right? So the questions it will tend to produce related to your queries will be such where it expects keywords to be present so that those keywords can be looked for in the documents and answers arrived at. Now, after that, we build a tree index. This is the most fancy thing there. And so when you are building tree index, you have, first of all, a GPT simple vector index at the bottom line. After that, you have a GPT keyword table index, which will use certain keywords. And then you are building a tree index on top of it. You are essentially composing indices. And these composed indices have, of course, the content, they are being built on the content from previous indices. So you have the vector indices which you created. So what is a tree? I mean, everybody knows that a tree is a structure which has branching. So you have one root node, then you have it branching out. You have two nodes or multiple nodes, and they branch out further. You have the finally leaf nodes. So to start with, you have a number of documents, and you want to, when you want to convert those documents into a tree, when you want to be placed within the tree, you would also need to come up with the total number of nodes in the tree. And in this case, the number of children in the tree, it's your length of number of documents plus 1, and length of number of documents, in this case, it's 3. But then, of course, you just don't need to store the documents. You also need to store more. You need to store GPT keyword table index, and then you would want to further build on top of it. So you will go with more children, and not just children, you'll have more nodes generally in the tree. So in this case, vector indices are being used, and of course, you will build on top of that only. But then when vector indices are being used, they are also being wrapped around with the root index, and the root index is using the keyword table indexes I mentioned earlier. So it is using keyword table index, and keyword table index will essentially help you filter out your query faster. So you specify the number of children, and then you specify the query config. Again, in the query config, you have those details as to what kind of structure is being referred to in the indices. And so when you, for example, in the physician case records, in that use case, which I demoed initially, I asked for top 5 cases. So that was an explicit provided number by me. That number was explicitly provided by me. But if you simply ask to show it the most relevant case, show me the most relevant case or most relevant cases, it still gives you an answer. So there is a top K limit, which either you can set from your side or it is set by the model, based on which it will provide you the answer. Now, this again is a part of the RASA code, where I'm essentially ingesting the content, which is input through my chatbot. But the relevant part here is that whatever I'm typing out, that gets ingested as content, and I have this outer graph. This outer graph is essentially made up of my tree index, where I'm using the root index, which is based on a table index, keyword table index, which is further based on GPT simple vector index. And I'm querying this outer graph. And the beauty is, because I'm querying this outer graph along with the content, I mean, I'm providing the content and query config and service context. And again, some of it is optional. I mean, I need not provide query config with that detail. I mean, the default can be used. And I need not provide a query transform either, but it helps to appreciate that. As in, for the demo, it helps to appreciate the importance of different parameters. So I get the response and then I print the response. Now let me see. Let me show you how it works out. How this is a double S word. So what I'm trying to illustrate here is the benefit, the pros and cons of using these indices. Now suppose I'll go to my chatbot. So this is the Ikai framework which we have, and I'll log in there. And I will ask it questions related to, so I have 3 documents related to Cigna, ATEC, and the third is Blue Cross. Let me ask it question related to Cigna health care plans. It's a very generic question. Now you would naturally expect it to return some answer because it is meant to be it's a general question, right? Now let's see what happens when you do that. And when I say it's a double S word. So first of all, it's starting from here. It knows that I'm talking about Cigna Healthcare. So when this tree was being built, there are at least 3 nodes which are related to different plans. And it knows that it has to go through one of the 3 nodes. It selects the node. So node 3 is seemingly related to Cigna, which is good. Now it selects the node and then it does a query transform. And the query transform here that you see as getting output is what is the deductible for Cigna Healthcare plans. Now I asked it a question, what are the features of the Cigna Healthcare plans? I am not asking it for what is the deductible amount for the Cigna Healthcare plan. It is coming up from its own side with this question. The idea behind this feature is actually to enable you to find a more relevant query. But in this use case, what is happening? That it is asking a question which is not so impressively relevant, right? So it, of course, it gives you an answer and it says, just let me just show it from here. The context information states that prescription drugs are covered in the Cigna healthcare plans. Therefore, this feature of Cigna healthcare plan is that they cover prescription drugs. Now, in one sense, this answer is not useful because I'm asking features in general. I'm not asking prescription drugs. But then what I'm trying to indicate here is this model, this LangChain is trying to convert the query in a format where it seemingly is intended to help, but is not helping in this case because the question which it has generated is not so useful for my purpose. Now, I ask it another question. Let me just refresh it. And again, this query transform is optional. One could do without it. And of course, in certain cases, it's best to do without it. But then what I'm trying to talk about is the theory of LangChain, where it essentially tries to see whether certain parts of the document can be more easily fetched by transforming the query. If I ask it to, for example, so here was a question related to one plan. It just went to one node and tried to do a query transformation, get an answer. But now let me just ask it to do a comparison between two plans. Compare and contrast. Okay, compare the features. I would rather go for, let me just check what the spellings. So 8-9 Blue Cross and Cigna. Okay. So I will go for 8-9 Cigna. Easier to type. Features and now I'm deliberately not typing the full sentence, and I'll show you why I'm not doing that. But let's first appreciate what is happening. So now it is selecting this node 4x4, and remember this node 4x4 is not necessarily meant to give you information only about one article. So what it is doing is when you ask this question, it comes up with two questions related to it. One is what are some specific features of Aetna health plan, and then there's another question, what are the specific features of Cigna health insurance plan? These are the two things which I'm asking it to answer on. And when it does that, it actually from my query, it sees which words are relevant, compare Aetna, Cigna, and features, and then it sees which are the keywords. Now, keywords are essentially which are expected to enable it to answer the question much more easily. With the keyword table index, it will be able to look for the relevant node and get to the answer faster. So in this case, it has only taken these as keywords. Now, there have been cases where I have seen where it fetches other words also which are not keywords, but that is where we can actually discipline it more by doing a further check by using either open source models or again chat GPT or GPT-3 and other models to essentially see that it's behaving in a desired format. Now, the answer which it gives is it's not possible to compare the features of Aetna. Let me go there. Let's just show the answer. It's not possible to compare the features of Aetna and Cigna, as only the specific features of insurance plan are provided in the context information. No information is given about the features of Aetna's health plan. No, it's still a good answer. So it goes to the relevant document. It sees that the specific features, right, are being only talked about in case of Cigna's health insurance document, and maybe Aetna's document is more general. It doesn't talk so much about the plans per se in that greater detail. So maybe if I go to this Aetna, so it's talking about Aetna health fund, health savings account. So the entire conversation is around a health savings account. It's not about quote unquote plans in that detail, right? Of course, in people who are in this domain would consider them as plans, but then you would need to rather maybe use a fine-tuned model, or maybe you would need to provide more prompts to make the model understand that it's a similar thing, if not exactly the same. But what it finds is that you have one document where you are talking about different plans in a more proper way, and you have another document where you are not, and it simply says that you just can't compare. Now, this is a good answer, but what I'm trying to emphasize here is that the way it generates the answer is quite interesting. So it once the tree index is built, you have a considerable number of nodes which are so there are some nodes which are of course related to your documents, but then there are nodes which will store the summaries. Then you have the root index at the top, which will actually work on those summaries. And when you ask a question, compare this versus that, it looks for the keywords. It with the help of those keywords, it navigates to relevant nodes. It splits your question into two or more questions. Here I just asked about two. Had I asked about three, it would have split into three questions. And again, this is being done using query transform. So it fetches the respective answers and it gives you the desired answer. So as I said, this is a double S word. One easier way of tackling it is of handling and getting a more accurate answer is not to use GPT tree index, because when you don't use it, you will essentially not to tree index you can use, but you need not use query transform. So if you don't use query transform, you are more confident that you will have a more realistic answer, because that intermediate level of LangChain enabling you to create an alternate query will not be there. You will just bypass that. So it's best to use in case you do not want to risk that, right? And most people would not want. So one way is you simply go for GPT tree, simple vector index or GPT list index or even tree index without this query transform. So you don't use that. But then there are cases, and I've seen that a number of times, where given that kind of domain you're working in, it's not always possible to map your question into the domain documents, and you need to have a transform in between. Now, it is where customization helps. So these are the cases where you would need to, first of all, to have another model, or maybe not even a model, a normal NL or Python program, or some normal logic implemented in Python, which will enable you to check whether the query transform is even relevant to your question, right? It's one thing to actually rephrase the question. It's quite another to change the very nature of the question. So when it asked about prescription drugs, I was thinking, where has it taken prescription drugs from, right? In the first question on Cigna. But that is what it is doing. The pre-trained model of ChatGPT is doing. So what I'm trying to emphasize here is that when we are using LangChain, so there are certain features in LangChain which enable you to be more efficient with respect to your token usage. So when you're using keyword table index, of course, it enables you to filter on your nodes much faster. When you're using tree index, it enables you to create, it enables you to do comparison between different sections of your documents much faster, which you would not be able to do with the list index. At that level of at that level of abstraction, so you can still pass and ask a summary related question, but then it won't be the right thing to do, because it will try to look at more details than what is required, where in tree index you will have those details abstracted out. Now only summaries getting compared. So that was it. I'm fully aware I've taken more time, but I think it was important to give a perspective to how these different indices work, what are the pros and cons, and how one can go about fixing them. So we did not deal with the fixes. Maybe we could do that in one of our subsequent discussions, but then, I mean, we didn't do an implementation of fixes, but then even more generally, when you look at these issues being raised on GitHub or elsewhere, and as you see the additions to the LangChain documentation, you see more and more ways of these getting solved. I mean, more and more people are working on these to fix them. Now, I have seen some 3 questions. I would like to answer them. So how do you evaluate the performance of an LLM based app, and what metrics are typically used to measure accuracy and effectiveness? So see, these the question is on LLM based apps, performance of LLM based apps. So it's a vague phrase. And why I say is vague, because performance would mean different things for different people. For some people, it would mean the response time. For a good number of people, it would mean response time. If you were to go by response time, and if you are using ChatGPT API, right, there are cases, especially during the peak office hours, I mean, morning, afternoon time, where you would find its performance very bad. So if you were to analyze that by the time, the response time, so that could be one of the feature. But then there are cases where you want to check whether the model's accuracy is higher. For example, not every time I want to run to retrieve a real-time answer by using an LLM. There are cases when I'm processing documents and I want to extract certain information from documents where I don't really need real-time inspection into that. For example, if I have a bunch of, say, 5,000 documents related to insurance or related to these research papers, and I essentially want to extract the summaries of those documents, I don't want to do it real-time. So I don't really bother so much whether it is responding to me in 1 second or 3 seconds, as long as it processes them in a considerable time. In that case, I will use domain accuracy as a benchmark. So it should not just output content from its pre-trained base. It should refer to the documents and create more relevant content, as in generate more relevant content. So my short answer to that question is, the evaluation of performance is based on the domain use case. If you are using it for a real-time application where you want output to be generated real-time, of course, performance is a key metric. When performance is so response time is a key metric in terms of evaluating performance. And when you do that, of course, for some people, performance for most people rather, you could make performance faster by using certain keywords, and you would be able to also appreciate whether in such cases you will be able to appreciate that in such cases your LLM or that index, that functionality in LangChain will be able to be used better, which supports this keyword nature. So what I'm trying to say is, when it comes to LLM models, the response time, the number of tokens which they consume are important features in general. But yes, there are cases where you don't want real-time inference, where you even don't bother about the number of tokens consumed. You only bother about the quality of output, and it depends application to application. So if you are using it as a chatbot, most people just use it as a chatbot. You want to run questions on certain documents and get the answers. Even if it is responding very fast, ADA responds super fast. But then ADA gives you nonsense answers as well in some cases, right? So you would want answers to be generated from your documents, and you don't want hallucination. Of course, I didn't talk about it so much, but then in general, I would like to mention that LangChain, Llama-Index, these are one of the best ways to control hallucination. You can't prevent, of course, completely, but then when you point to specific documents, and it gives you the answer that there is no context in this document related to this question, you at least are confident it's not at least be fooling me. Next question is, I would like to summarize the documents and also create a bot to answer questions. Does the demo show works for both cases? Of course it does. So see, well, partially I've just, as I've been discussing, I have demonstrated that. So when you, in this case, we are just using GPT tree index, keyword table index, and simple vector index for answering questions. But then in that process, you also do a summarization. That's one. Point number two, there is nothing which actually prevents you from asking it, from using the prompt, summarize the document for me, right? It will still do that work. All what I tried to say was that if you have to ask, get multiple documents compared, there are more efficient ways of doing it. Where, I mean, you could use tree index, for example, for that. So it will compare at the level of summaries rather than going to details of each document where you don't even need them. So are you using context and story in Rasa? I hope you're not using any functionality from Rasa, but from OpenAI in this case. So, well, in this case, I did use the NLU functionality from Rasa, but also because the objective was not to recommend or rather suggest LLM for intent classification. So LLMs can be a very good use case for NLU and Rasa, whereby you actually do intent classification using LLMs. But I've also seen is when you have more simpler cases where you anyway know you have a limited number of classes and it's easier to classify, why should you even go for an LLM? You should go for an LLM in cases where you understand that output is tough to generate, right? Classification is a simpler problem. And if you have almost binary classes, right? Or even ternary classes, you don't really need an LLM for that. The worst part of using an LLM is it can be slow at times, right? And if I were to use ChatGPT in this demo for doing intent classification, you may not even have got the answers in reasonable time. The third question is, this still limitation on the context, right? If we have 1000 page PDF, we won't be able to search as well as we'll be running into context limits. Well, I think Scott mentioned in the beginning of this webinar that the way these models, this framework works is, when you ask a question, it looks for the relevant content in the set of documents and passes that content to the model. So if I ask it a question, what does the Cigna Health, a particular Cigna healthcare plan offer for elders above maybe 70 years of age, right? So when this question is processed, it is converted into embeddings. The embeddings of the vector embeddings of the document are retrieved as well, and there is a similarity evaluation done, and only the relevant embeddings are passed to the model. At the end of the day, you are right that at any point of time, an LLM model will still be able to ingest only a limited number of tokens and produce a limited number of tokens. But that said, what LangChain or Llama-Index are enabling you is, first of all, they are enabling you to pass only the relevant context. That's first. And then it's not just a one-time or one shot passing of the content, right? You can do it in loops. You can actually, if you want to for example, if you have to summarize a 10,000 page document, you of course don't pass that to Llama-Index directly to summarize, right? You split it into different indices. You take each index, summarize it, and do that for a couple of indices together, then build a query on top of it for doing further summarization. LangChain enables you to do that kind of manipulation much faster. But at the end of the day, your LLM will, as far as your LLM is concerned, it will see some specific content only within its limit. Next question is, what is the difference between Llama-Index and LangChain, and which one to use? So LangChain has so LangChain you could consider as a superset, and Llama-Index as one implementation of that. So LangChain is a more is a greater concept. It's a greater framework where you, for example, earlier this was known as GPT index, right? And that GPT index was getting evolved almost independently of well, at least in the initial days of LangChain. It was built on top of LangChain for sure, but then its evolution of independent was more or less independent. But then ever since this Llama came into picture, the model came into picture, right? And when they have started, when they revamped the documentation, so you see a more closer kind of synchronization between the two. So what I'm trying to say is, you don't use LangChain. It's not a comparison between LangChain and Llama-Index. These are not two different things to be compared. As in, Llama-Index is built on top of LangChain. So there are cases where you would see that other features of LangChain are more useful to you, not Llama-Index in particular. You would go for other features of LangChain. So I don't think it's A versus B. It's about when to use the A feature of B and when not to use the A feature of B. So for example, if you only want to, well, there are cases where you wouldn't even want to use Llama-Index for that matter. If you were to ask a more general question, should I use a ChatGPT API or should I use Llama-Index for answering a given question? My answer would be depends on the use case, right? It's no use using Llama-Index where you can get your question very quickly answered because you have a smaller prompt. I mean, so you would go for Llama indices, you would go for LangChain when you essentially have big documents, huge databases, APIs where you want to fetch information, reorganize it, etc. If you only have some specific small document, etc., you can even pass that as context to the model and it will still retrieve good answers. So I see the questions, these were the questions which I had. So
right. Thank you, Shubham. I think those are all the questions that we have for today, but there are quite a few that we have answered during the course of this session. So thank you once again, and thank you to Abhilasha and Scott also, and to all our attendees. Thank you for being so patient. We have gone quite a bit over time, but I hope this session was insightful and helpful as it has been in the past. So thank you everyone, and we will be reaching out to you for more such sessions. There are quite a few planned around similar topics in the coming months, so please keep a watch on that, and we'll see you soon next time. Thank you.
Yeah, thank you.
Thank you.
thanks everyone.